I thank the organizer, in particular Massimo, for the kind invitation. I have also a disclaimer, like the previous speaker, whom, by the way, I thank very much, not only for the real nice talk, but also for having prepared much of the ground which we'll be needing here. And so I would also say that here topology is concerned in a broad range. We will see, I will add a couple of comments, which I will not have real time to explore, to fully explore. Still, we thought, together with Massimo, that this is a nice thing to have a look at in this context, related to also what the previous speaker told. For sure, we are in extreme environments, and we will see there are relationships to topology as well. This work is done in collaboration with people in Parma, but also with people in Bielefeld in the framework of the Europlex network, a research network, which I'm happy to acknowledge together with Strong 2020, which is the European research network, which is supporting all of us in these days. So what is the idea? The title had to do with the complex plane. I think we all do the same. We teach students that usually it's a good idea not to think of complex functions as the extension to the complex plane of real function, but to go the other way around, right? So real functions are the restrictions to the real axis of complex function. Still, when something complex from time to time pops up, we are sort of annoyed. So I stole this from a joke by Jana Gunther, who was telling, well, I've always been told the complex plane is the real arena. Then we face a complex action and we are pissed off, okay? This is true, and this is mainly true due to the sign problem we were told before. But still we think that in the end, we have to go to the complex plane in order, for example, to fully appreciate what is the structure of a phase diagram. So we will be concerned with Lefschetz Timbal, and this has indeed a strong connection to topology, which I will tell you again, I'm not going to go, right? But it could be thought in the background. And then we will move from something which we learned in Parma from Timbals to something which is an application to the study of the phase diagram of QCD. And the unifying tool is going to be Pade analysis. So let's go for a real quick introduction in a nutshell via a toy model to Timbal. So suppose you have an integral like this. Here, the only thing we want to point out is that the action is complex. And thus, we have a sign problem. We can't simulate directly by Monte Carlo something like this because we lack a probabilistic interpretation. So what can we do? What is the solution provided by Timbal? Timbals in this context were by our group, Parma and Trento at the time, Luigi Scorsato and Marco Cristoforetti were involved as well. Basically started from a paper by Witten. And then we realized that at the time, Yoshua Kikukawa and collaborators in Japan, they were doing exactly the same thing. This is one of the funny situations in which two groups are doing exactly the same. And that's why I always advertise it as something which came from us and from them as well. What is the idea? As you can see, I'm rewriting both the numerator and the denominator, which is the partition function. Instead of one single integral, I have a sum of integrals. The sum is running on an index sigma, which we have to thought of as sum over stationary points. That means points where the action is an extreme, right? As you can see from the notation, we switched from the X notation. It is only a towing model, right? So something like a summary, a sketch of what is going on in a realistic situation. But now the degrees of freedom is written as Z. So you have to think of that as a complex degrees of freedom, right? Which means you have complexified, in a sense, your system. And then attached to each stationary point, there is a thimble. We will see that is a stable thimble. And that is the union of the solution of all the steepest ascent equation, this one, which we can integrate with an initial condition which is sitting at the stationary point, right? So that is the reason for the name thimbles. If you think about that, there is a tip, and then out of that, many lines making the thimble going up, with the action increasing. But beware, the real important point is that on each thimble, the imaginary part of the action stays constant. And that's why in the integral, the contribution which is coming from the imaginary part of the action is going out, and it is a constant in front. There is indeed one thing, which is the so-called residual phase, which has to do with the orientation of thimble in the embedding manifold, right? I'm not going to spend time on that. But what is the message? We went from a single integral to a sum of integrals, both for the integral at numerator and at denominator, which is the partition function, right? And we are taking a sum of integral, all of them computed attached to stationary points, okay? Then one first notice with respect to topology. In the case of gauge theory, everything is much more involved, and we don't have a real proof. We have been working, and we are still working on a simple setting, which is 2D Young-Mills, where there is something which is very close to a thimble decomposition, but we are still formally working on that. But in any case, if you had to think about something like that, instead of stationary points, in that case, you need orbits, right? So all the gauge transformation of a single stationary point. But the important point is that the thimble is always defined that way. So you ascend from the orbit, and in ascending, which is in paving your way and in constructing the thimbles, the value of the topological charge stay constant, simply because all this is made out of the equation of motion. So by definition, it stays constant. So that is in principle a way of computing completely disconnected contributions, which are different because of the different, also because of the different value of the topological charge. So they have a signature with that respect, okay? This is very interesting and very much related to the workshop, but I'm not going to talk about that at all. Sorry for that, right? So what we are concerned of, as you can see, this is a sum. So you are trading a difficult problem for another difficult problem, which is you have to compute many contributions, okay? Having said that, one can rephrase this as a sum of something which is really something like a new path integral attached to a single thimble. And you have to compute a superposition of that, of those, right? So what is the idea? So let's take this, this is a real toy model, is only 0 plus 1 dimensional if you want. So this is a would-be 5 to the 4 theory, but in 0 dimensions. And this is a plot which is telling you what's going on. So these three are the three stationary points. As you can see, there are blue curves and red dotted curves. The reason being that there are stable thimbles, and those are ones which are here taken into account. But at the same time, we have unstable thimbles. Simply, instead of computing solution of steepest ascent, you compute solution of steepest descent. So on stable timbal, the action is always increasing and the convergence is guaranteed. On unstable timbals, the action is going the other way around, decreasing. And so you're lost and you lose convergence, okay? As you can see, here it is easy to see what is the original domain of integration, is the real axis. And it is easy to see, to inspect, that this single timbal attached to the dominant stationary point, which is the origin, is a smooth deformation of the original contour of integration. So it doesn't take timbal to understand that you can compute the very same integral on the blue curve, right? Notice that this is in agreement with a general rule, which is a timbal is to be taken into account in the combination only provided the unstable timbal associated to that point crosses the original domain of integration. Now, the main message is the following. Look at all these timbals and you will see they always have to stay away from each other. So they cannot cross each other. That's the point.
Can I ask a very stupid question?
Yes.
This action, where is this complex? The sigma or the lambda is complex?
Sigma. Sorry. Sigma is, of course, you don't want to have to screw up things with lambda. Sorry, Daniel, you're absolutely right. I should have written that. Right? So you talk several times about that, and you always try to condense, and then you end up with something which some missing information is missing. Sorry, interrupt at any time. I know this is a sort of bizarre, so please feel free, right? Okay, so the idea is that, again, these curves, they can't cross each other. And that's why they act, in a sense, as topological barrier to each other, okay? Which means that if this is enough to take the whole contribution into account, simply because the other are completely disconnected. They simply can't be deformed into the original domain of integration, right? This is the main idea. This is the main idea behind timbal decomposition. So in principle, I should take into account all the timbals, but only those attached to critical points whose unstable timbal crosses the original domain of integration, only those are to be taken into account. So one here is very happy because one single timbal is enough and we are done. But of course, I'm cheating you, as you could imagine. The problem being that the timbal decomposition does not hold the same once and forever. It is a function, quote unquote, of the parameter of the theory. Again, Daniel, depending on sigma, you can have different situations. So first situation is what we saw. One single is enough, and the interpretation is quite easy. Deform this and you will find the original domain. Here is an example in which more timbals are contributing in a very, very simple-minded way. You see, by doing this, and this, okay, I reconstruct the original domain of integration. The good point is that there will always be a combination of timbal doing the job for you, right? This is the good message. The bad message is that maybe I need more timbals, okay? I'm still cheating because you can get a Stokes phenomenon, which means I was telling you timbals, they can be stable, unstable, they can't cross each other. There is one single way they can cross, okay? So how can I deform these into these if they can't cross? The reason is that at some point, the stable timbal can go on top of the unstable timbal of someone else. In that case, basically, I simply miss the timbal decomposition. That is the Stokes phenomenon, okay? So you go from one situation to another, going through Stokes phenomena. That is the main message, okay? At the very beginning, we were very keen on the idea that by a few arguments, basically in a broad sense of universality, a single timbal dominance could be a good idea. And there are indeed cases in which you collect the relevant contribution only from one. But the idea is that that in general fails. It holds true only in given cases. And one gentleman in the audience were among the first who proved that, and that was the case of the Turing model. Yoshua Kikukawa and collaborators, Andrei, together with Paolo and collaborators, so they also made the point. So what is the point? This is the action for 1D Turing. As you can see, at given value of the, here only one single timbal is taken into account. A given value of the coupling, that is fine, but at some point it starts failing. So what do you do? Well, there was this hypothesis, well, taking into account more timbals, it should work. And indeed, that is the case. And indeed, 2 single timbals is enough. This is the way out in this case. This is the, how to say, very, very tedious way out, in which you compute 2 timbals and you surrender to the idea that you take one point as normalization point. What I mean is that I condense all my ignorance about the combination of timbal in one single parameter. So I have 2 timbals, I have arguments to say that they should be relevant. I compute one observable and I fix this parameter, and then I'm predictive on others. Okay, but this is not what we want to do. And the main message is the following. The main message is that while timbal decomposition is discontinuous across top phenomena, physical observable in general are not. Which means, first idea, well, compute Taylor expansions on timbals. That means look for regions in which one single is enough, compute Taylor expansion, and then you bridge, taking together the 2 expansions. Immediately after that, you realize that there is a better way, which is you have Taylor expansion, so you go through multi-point Padé approximant and you bridge. And that is what you get, right? So to make a maybe longish story short, here is a point where one timbal is enough, and it is quite easy to argue why. Also here you can argue, there is a little bit more of elaborate thinking behind that, but it's still reasonable. Also here, that is enough. So you compute here, no sign problem, here, here, and here, when single timbals are enough, and then you bridge by Padé, a multi-point Padé, as you will see. What is an extra bonus? Look here, you know that the solution, which is analytically known, has a singularity. And you can gain understanding of that, I mean, gain knowledge of that. The singularity which you get from your Padé is just going on top of the known singularities. This is a very, I have to say, clear and lucky, if you want, situation in which you can see that the Taylor expansion themselves could be enough, right? Because there is an overlap in between the 2 convergence regions of the 2 which are involved, okay? But once again, why is Padé a little bit better than Taylor? Because Padé is encoding singularities as well, because of the denominator. That is the main message, right? So, in the end, because of that, we were also able to go to the continuum limit. So, the solution, in the end, was solved within the timbal approach. But now we want to do more. So, what did we actually learn, which we can take and maybe make it useful in the QCD phase diagram arena? So given the same problem, what can we do? We know, thanks again to the previous speaker, Taylor expansion at 0 mu b are fine. Also, observable computed at imaginary value of the chemical potential, those are fine as well. So the idea is we do like before. Before we had different points where single timbals was enough, Taylor, Taylor, and Padé. And here we do the same. Mu equals 0, many other values at imaginary value, many points where we are fine, and we do Padé on top of those. The idea being that we compute cumulants of the net baryon density at a number of imaginary values of the chemical potential, including 0, of course. And then we do Padé, which means we approximate that by rational function. Here, there is a slope notation maybe. Here is only a function of x. What we mean is that T is fixed, we stay at a given temperature, V is fixed as well. The dependence on mu comes as a mu over T dependence, one single variable, which is your x. And then you compute a rational function approximation, which means, given the cumulant nature of that you write, in a sense, the Padé approximation for chi1, but that also encodes all the other cumulants by differentiation, right? Okay, so all the coefficients are constrained by your measurements on the cumulants. Remember, we have in mind this, and this is our Padé approximant, a polynomial at numerator, and at the denominator, you can get rid of one parameter, so you rewrite at the denominator 1 plus a polynomial starting from first power, okay? Which is very convenient, because then if you want to reproduce a given function f and its derivative, you end up with something like this. You see, at the first point, x1, the fact that Pmx1 divided by 1 plus Qn of x1 is equal to fx1 can be rewritten this way. And you go on and you rewrite for the different derivatives and for different points as well. What is this? Is a linear system. On the left-hand side, the dependence on the unknown Aj and Bj is a linear dependence. So this is a linear system to be solved, right? There are alternatives. So one alternative, for example, is to slightly change the form of the rational approximation. In this way, I'm guaranteed that I'm getting for chi1 an odd function as it should be, okay? Another alternative is, instead of solving the linear system, by the way, that is quite often not that well conditioned, but you can perform the computation. If you don't trust that as much, you can think of minimizing a generalized chi-square, okay? That's another way of solving for the coefficient. Okay, having said that, what do? So 2 plus 1 Hisk fermions. Bielefeld people are, of course, the masters here. You can't rely that much on Parma for that, but Bielefeld, they have all the machinery. We go close first to the Robert Weiss transition. Once again, we know from the previous speaker, and we focus at the beginning at n tau equal 4. I'm not taking the other dimensions into account, simply because they are fair enough. They are large, so there is a factor of 6. So 4 times 24 to the 3, and then we will go to 6 times 36 to the 3rd. So our lattices are coarse, but they are not small, okay? And these are simply our measurements. So this is the imaginary part of chi1, then chi2, then chi3. And as you see, everything is as a function of the ratio mu b over t, which is imaginary, okay? Here there is no fit, nothing whatsoever. So the dotted lines are only there to guide the eye, okay? As you can see, of course, by going to Eiger and Geiger derivatives, your signal is deteriorating, right? But you can manage. And of course, most of the information is in a sense coming from this, but also others are supporting us and providing information. So what do? In the end, you want the rational approximation to hold. And here we go. As you can see, these are different temperatures, okay? So we start from 167 MeV, and we go up to what is known to be Robert Weiss temperature, which is slightly above 200 for this setting. Those are the black dots. The rational approximation works very well, but of course, here you know that there is something going on. That is Robert Weiss, and that is simply signaled by that. Notice that there are extra peaks, which are harmless. I can tell you. I will tell you then why. But the main point is we can go through our data via the rational approximations. Okay? So one funny thing you can immediately do is to integrate and go for the free energy. So this is the very close to what is the usual cartoon which we plot, right? Near the transition, one expects a Caspi behavior, which is what you get, provided, of course, that you are still on a finite volume, okay? Which is nice, okay? This is exactly the expected behavior. Then you can do, of course, more, which means we have an imaginary mu, our rational approximation, and we can get an analytic continuation. So this is right in the spirit we were told before. We need a way to transfer information for imaginary mu to real mu, okay? Having this form, you can think of a candidate for your analytic continuation. Look at this, imaginary part should be 0, of course, for real mu. Is it 0? Well, the main point is, look at the red, at the green, that is absolutely 0, right? I'm not cheating, I'm cheating in a sense, because that's the odd function. And in that case, we are guaranteed we are going to get 0. But even if there is no constraint, as you can see, till this value, at least, of mu, of real mu, the imaginary part is absolutely 0. And then start deviating. But let's say that up to here, there are a couple of confirmations. One is that, okay, different temperatures returns different continuation, but different methods, for example, chi-square, solving the layer system, and so on and so forth, different orders in Padé, they are roughly consistent with each other. They are quite well consistent with each other. Is this the only thing we are interested in? We have already seen spikes over here. So this is the expected one, the transition, right? But I also pointed out other minor spikes, okay? So the idea is that we are starting feeling the singularity structure. So in the end, we are hunting for Lie-Yang zeros, which are zeros of the partition function, okay? This is a picture, a slide which I took from Christian because I like it very, very much, right? So this is the standard way people in Bielefeld write the phase diagram, if you want, in 3 dimensions. This is T, this is mu, and this is the mass, okay? So all these curves are curves we are interested in. Here, this is the chiral transition. Everything is well known over here. Bielefeld, Wuppertal. Now we know what's going on at mu equals 0. Crystal clear, no transition, crossover. But then we switch mu on and we want to see what's going on. This is the guy everyone is looking for, the critical point. But there are also transition as you, that curve evolves as you change the value of the mass, right? Over here, so here we go to our... I can go on. Okay. So this is our complex mu plane. Okay. Look here. There is something orange plotted, which I couldn't plot here. And this is right, what's going on in terms of the Roberts-Weiss transition, which is there because of that Z3 symmetry, which is there for the mass going to infinity. Okay. So here also we know something. Thank you. This guy over here, a line of first order transition when the temperature is high enough, which means higher than Roberts-Weiss temperature. And then we know that everything should be connected here, so that at some point I should join also with what is going on for real mu. This is the standard plotting, which you plot in terms of mu square. So imaginary means mu square negative, real means mu square positive. I have to say I'm very grateful to Maria Paola and to Massimo because the first time I got this was when a few years ago we were I was involved together with them who mastered the idea in simulation at Imaginary Mu. And this was exactly the plot we were drawing at that time. Okay, so thank you, Maria Paola and Massimo, for that, for having involved me in this stuff. This is what we get. Okay, how? These are the. This is a plot of zero of numerator and denominator in my rational approximation. Okay, what does it mean? It means it's very simple at this point, knowing the coefficient which have been fixed, to look for zero. Okay, so with some sort of abuse of notation, we call them zeros and poles. Okay, so zeros at the numerator are zeros of the function, zeros of the denominator are pole of the function, provided there is no cancellation. Okay, but this is the point. As you can see, there are lots of cancellation. So the relevant information is coded where, looks for example here, these are genuine poles. The zero at denominator is not cancelled by the zero at numerator, right? And it comes with the expected replicas, okay, because of the functional form. Okay, so once you get 1 0, you should find then 4 0, and you do. Okay, there are also 0 which are expected. Those are on the imaginary axis, and you get it. Then there are many other zeros, of course. Given the degree, you know how many zeros you will find. So are all of them relevant? The answer is no. Most of them exactly cancel, as you can see, between numerator and denominator. First line refers to different temperature. This is the closest to Roberts-Weiss. So beware, one should expect something which is fooling you, right? Because you can get pole from Padé, but you can't get a cut, right? But if the Padé is high enough in degree, you can mimic a cut, and that is a cut. That is what is known from Padé, which means you end up with a sequence of zero and poles. Andre?
So if you have the coincidence between poles and zeros, that means that your polynomials are factorizable, no?
Yes, exactly, exactly.
So why use that? Why not just factor out the common polynomial?
In principle, you can once you find, right? So the point is that solving for zero is the same thing, but it's most intricate. Once you know, you can, if you want, collapse your information into a lower degree ratio.
Yeah, but wouldn't that, if you try to actually fit this many parameters, you also can only get a lot of noise because you're actually, these are unstable.
The point is, how many zero can you get? That's the point. Okay, you will end up with something which is as complicated as this. You could stay with a low number, and then someone could come and tell you, why do you stop there? Put more. You put more, you suffer more, and you end up with a picture like this, only in a more difficult way. But that's the point, right? You don't know a priori. So a priori, in principle, you should say the real Padé is the one where there is no cancellation, but you don't know a priori. That's the point. So you get all your information and see what you can squeeze. This is something which should be elaborated more than this, but I don't have time. Maybe in private I can tell you more. Okay, but the main point is, just to progress, second row, same temperatures, right? But different functional form. Okay, as you can see, the relevant information is still the same, but the cancellations are different. Okay, so there is a clear cut in between relevant and not relevant information. Thank you. This is also fine. You can go to the fugacity plane, and the picture stays the same. This is very important because in the fugacity planes, the setting you end up with is a safer one with respect to relative location, which means how you can constrain your Padé. Again, I don't have that much time, but trust me, this is very important. Then if you read the papers by Gerhard, Gunn, Gotche, Lazar, and collaborators. They have a proposal to do this systematically, right? Okay, the point is, shall we trust all this? And this is going back to the previous slide, if you want. So we know there is something going on in the phase diagram, and we know that we can get, in principle, scaling relation. So we are close to a second order transition. We can identify the scaling fields, and in the end, we can solve for the real part of the mu corresponding to 0, the imaginary part being constrained to pi. And we do find that. Do you remember? In our plot, the imaginary part is pi, okay? And as the temperature rises, the real part goes to zeros, eventually pinching I pi, which is the expected location of the transition, right? So this is very nice. We can indeed fit those scaling relations. This is much better for n tau 6, and we are still in progress with extra data. We can fit value for the Roberts-Weiss. This is something which goes close to previous determination. Then if you are really brave, if you were my students, I would tell you in Italian, questo è un po' Corsara, then please ask Italian people what it means. But okay, the idea is that previous work had showed that even n tau equal 4 is in the scaling region, apparently. Then if you trust that, you can be really a little bit, maybe too brave, take and extrapolate, and you get something which is consistent with what other people got. Okay, but the main message is that this can be systematically improved. Okay, then in order to finish, because I'm running out of time, in my original plot, there were points on the Roberts-Weiss line. This is our first guess, well, preliminary result for something which could be a chiral transition. Okay, that is compared in terms of confidence level with a result which is coming from RG theory, independent of anything, well, getting information from lattice result. But the idea is that here there is no fit. So there was if you want, a forecast number to compare with. Okay, this should be a little bit cleaner than it is now. So stay tuned for that. So what are my conclusions? Well, the end, complex plane is a good arena for all of this. And multipade analysis can be a nice tool with this respect. I try to convince you that the combination Timball plus Taylor plus Pade is a good one to gain understanding. Who knows, maybe at some point we will be able to go for QCD as well. At that point, topology will be really very relevant, right? As for what we can do now for QCD, by computing many value at imaginary chemical potential and derivatives on top of that, cumulants, we cook everything together in Pades, and we end up with a study of Lie-Yang singularity. The all gray, as you can guess, as for everyone, would be the critical point. We are admittedly very far away from that, but you always hope, okay? And that's all. Thank you.